Well, hi everyone, Mrs. Hanson once again, wrapping up some topics on resonance in Chapter 2. We've left off here with Chapter 2, Section 10, which is called Resonance Pattern Recognition. And we're going to learn that there are 5 general bonding patterns in which resonance structures can occur. And you must recognize these patterns in order to predict if resonance will indeed be present. So they're very critical. And that's going to take some practice. So we're going to start in and practice each of the 5 together. The first of the 5 patterns is an allylic lone pair. Now remember what allylic meant for us? Allylic means that we have this double bond, the 2 carbons in the double bond. It's the position adjacent to it. So this is the allylic position. And if it has a lone pair, you're looking at saying a pair of electrons right here. Second one, an allylic carbocation, which would represent a structure in which in the allylic position, there's a positive charge. A lone pair of electrons adjacent to a carbocation. So let's say we have a position where we have a set of dots next to a carbocation, a pi bond between 2 atoms with different electronegativities. That could be, for instance, a double bond between a carbon and an oxygen, for example. That's a different electronegativities. And the 5th is a conjugated pi ring. So, for example, our aromatic compound, which we're learning is benzene, where you have a cyclic structure that alternates double, single, double, single, double, single. That aromatic compound are called conjugated pi bonds in a ring. So the only way to recognize these patterns, as it says, is to do lots and even more practice problems and examples. And that's my goal today, is to work some of these problems and provide examples with you. So pattern number 1 talked about the allylic position. And let's just remind ourselves of these 2 definitions. The vinyl and allyl refer to atoms of the pi bond and next door to the double bond, respectively. So let's say the carbons involved in the actual double bond are in the vinylic positions. These 2 carbons are involved in the bonds. Whereas the carbons adjacent to the carbons involved in the double bond are in the allylic positions. So with this structure, I can see that there would be 4 allylic positions. We look for allylic lone pairs because they will exhibit resonance. So remember rule 1, the pattern 1 said look for an allylic lone pair. So the first of the 5 general patterns says if we find a double bond, look in the position next door and see if they have a double bond, a lone pair of electrons. We look for the allylic lone pairs because they will be in resonance. They will be delocalized. So for example, I had written on this earlier. Let me erase that. Here is a carbon to carbon double bond. All right, so we know the carbons that are in the double bond are known as vinylic. We're looking for the carbons that are adjacent to that. So this is an allylic position, and this is the allylic position, directly next to the carbons in the double bond. Do you see any lone pair electrons? And the answer is yes, right here. Notice that this lone pair is too far away, so that's not the allylic position. It's not directly next door, but 2 steps down, that's no good. It has to be directly next door. So we have a set of lone pairs in the allylic position, which means it can exhibit resonance. If I just back up, what that means is that this lone pair can go here and these can go here. And we can just start moving the electrons around. All of the lone pairs drawn in the examples are allylic. So let's just focus on that definition. Here's the 2 carbons in the double bond. So the position that is 1 away is the allylic position. Here's the 2 carbons in the double bond. One carbon or one position away is the allylic position. That has two sets of electrons. One would be delocalized, one set would be localized. You're only allowed to move one set of electrons, not both. Here we have a double bond. The positions of the double bond, one position away would be the allylic position. Again, that meets the criteria. It has two sets of electrons. One would be localized, one would be delocalized, available for resonance. Here is a double bond. The allylic position is one position away. That carb anion contains a set of dots available for resonance. And one more time, here's a double bond, one position away. Here's a set of lone dots. Oops, I missed the color coding. And that would be available for resonance. And that's exactly what we've shown you one step at a time down here. Here is the allylic position of this carb anion. The set of dots becomes the bond. And the resulting structure ends up moving the positive charge to the left and the double bond to the right. Here, the resulting resonance structure would have the oxygen losing a set of electrons, forming a double bond, the double bond forming a set of dots. Again, remember to consider the formal charges as you develop your resonance structure. In this structure, the set of dots is formed from the pi bond, making the oxygen negative. And this oxygen moved a set of dots to make a double bond, making this guy 1, 2, 3, 4, 5, he ends up positive. And here, this double bond goes up to the nitrogen now as a set of dots, two sets of dots. It now has 1, 2, 3, 4, 5, 6, so it will have a plus formal charge. And this down here became a double bond, 1, 2, 3, and this had a hydrogen, so that's all set. 1, 2, 3, the third one was a hydrogen, so that hydrogen is still there, so no formal charge. And the resulting resonance structure here, I have 3 sets of dots now on the oxygen, making it a formal charge of -1. The nitrogen had a set of dots. Oops, let me clean that up. The nitrogen now has a pi bond. 1, 2, 3, 4. It would like 5, so that's now a positive formal charge. All right, so just remembering as we move electrons around, forming the resonance structure, always include formal charge. When the atom with the allylic lone pair has a negative charge, the charge is delocalized with the lone pair as shown here. And those, my friends, are the very things that we practiced on the previous slide. We were just moving the electrons around from one position to the next. So if a set of dots becomes a bond, the bond becomes a set of dots. The pi bond becomes dots, the lone pair becomes a pi bond. Dots become a pi bond, pi bonds become dots. Pi bonds become dots, lone pairs become bonds, and so forth. It's just reminding you when you write out the new structure to always write the formal charge in the new resonance structure. So shall we practice? Draw the appropriate resonance structure. So let's put on the number of dots we know are there. A pi bond can become a set of electrons. And when we're doing so, we have, whoops, this oxygen's in here. A set of electrons forming up here. Now, why didn't we do anything with this other oxygen? This other oxygen has a set of lone pairs that's also adjacent to that pi bond. So here's a set of lone pair electrons. So I could move the pi bond and create an O negative up there. But there's also another opportunity to move that pi bond, except it would develop more formal charges. Let's kind of take a peek. If I move the second lone pair, we get an oxygen with a double bond and a positive charge. So just wanted to kind of verify this also works. This meets the criteria of having a lone set of electrons in the allylic position. So this can also occur. And when it does so, you form a double bond here. And now you have a positive formal charge. So two arrows, because there are two allylic lone pair electrons. Here's a set, and then the second that meets the same criteria would be here. All right. Draw the appropriate resonance structure. Well, all right. This means that right here is a negative formal charge. So that's 1, 2, and we need a pair of electrons here, 3, 4, and then there's a hydrogen. Even though it's not drawn, we know it's there. So our pi bond is the allylic position. Right here is the allylic position. And it has a set of lone pair electrons. Even though they're not shown, we know they were there because we see a negative formal charge. That means that the electrons can become a bond, and the bond becomes a pair of electrons. And when we redraw that structure, the pi bond now is between those two carbons, and the lone pair has moved out here. And remember, that would be a negative formal charge. So we've moved a set of dots by removing the pi bond. And that's what we've shown in that particular structure. You place all the lone pairs on the structure. You locate any lone pair that's in the allylic position, and you draw the arrows to convert from one structure to the next. Try another. Okay, so I'm going to start by drawing all the lone pairs on the electrons here, and the oxygens have, I don't see any formal charges, so which means, the formal charges, they're all going to have two sets of dots on the oxygens. All right, let's find the double bonds. Here's one. Do you see any lone pairs in the allylic position? And the answer to that is no. So these are localized electrons. They are not in resonance with anything. All right, so that's off the plate. Here we have, I'll just pick a different color, go back to highlighter. Here is our double bond. Do you see any lone pair electrons in the allylic position? And the answer to that is yes, right there I do. So we have an opportunity to exhibit resonance. Alrighty. So we're going to delocalize that electron. Remember, one of these is localized, and one of them will be delocalized, one set I'm referring to, because you can only move one pair of electrons in resonance, not both. So when we move this set of electrons becomes a pi bond. The pi bond becomes a set of electrons. And we get, on the other side of that arrow, here's where we had the original oxygen that was not in position to exhibit resonance. Here, the oxygen will now have a single bond, 3 sets of dots in the negative formal charge. Down here, the OH lost a set of dots and moved to a double bond, resulting in 1, 2, 3, 4, 5 assigned electrons. So that's a positive formal charge. We got it. That matches our screen. Oops. Oh, the USA. Let me silence my phone. Here's the second of our 5 patterns, the allylic carbocation. Only one curved arrow is needed to show resonance for the carbocation. And again, we're just moving the pi bond to become in the other position so that the next positive charge moves to the other side of the allylic carbon. And if there's multiple bonds, which are called conjugated, then multiple contributors are possible. Notice that conjugated means alternating single, double, single, double, single, double. That's conjugated. But only move one set of arrows, only move one set of electrons at a time. Only move one set of electrons. And that way you'll remember to get all the possible resonance structures. So here we have just to highlight, here is your double bond. And here is the allylic position of the positive charge. That means in the first movement, I've moved the pi bond between carbon 1 and 2, and I've moved the positive sign to position 3. Now I can see that this next pi bond meets the criteria to this allylic position, and I can move that then one more time. I only move one pi bond at a time. So draw the possible resonance structures here. So the first pi bond that is in the correct proximity to the carbocation are those two. And so remember, I can move one at a time. So this pi bond is going to move towards the positive. And what happens when I redraw? The pi bond is now here, and the positive is now here. And this bond then is still located in the same position. Now I meet a new criteria that this pi bond is in the correct position, the allylic position, for a second resonance structure. So I can add yet another arrow, and I'll move the pi bond, and then the positive charge results on the next carbon. Let's see, this guy stayed in the same place. Double bond moved, so now this carbon results in the positive charge. We had 3 possible resonance structures in that conjugated double bond. Conjugated means alternating double, single, double. We got it. Third pattern says a lone pair adjacent to a carbocation. Here is a carbocation. Notice that's an empty p orbital. It's an sp2 hybridized carbon, which means that empty orbital has room for a bond. So I can turn it from sp2 to sp3 with a resonance structure. Here is an empty p orbital. So this carbon is sp2. It has room to accept another set of electrons, another bond, to become an sp3 carbon. So recognize that the formal charges are affected, obviously, but you can move electrons into a carbon that has an empty orbital, and that's all it's saying. Carbocations have empty orbitals, so you can move a pair of electrons to give that carbon a 4th bond. So what might this look like? Here is a nitrogen with 1, 2 assigned electrons, 3, 4. So now look, if I take this and I draw a circle, here's 1, 2, 3, 4, 5, 6 assigned electrons. Nitrogen lives in group 5, so that's where the -1 formal charge comes up. So remember, even though they're not there, I know there's 2 sets of dots on that nitrogen. And this right here is an empty orbital on that carbon. So what does the resonance look like? Let me clean that up, I guess. Just put on the pairs of electrons. And then you can see I'm going to move one set of electrons to make a pi bond. Nitrogen still has 1 lone pair. It's leading off to another carbon. It now has a double bond leading to a carbon like this. Actually, it should be like this. The double bond is between carbon like this. That's better. All right, so what about formal charges? The nitrogen, who still lives in group 5, has 1, 2, 3, 4, 5 assigned electrons, no formal charge. This carbon still lives in group 4, 4 assigned electrons, no formal charge. So there's no positives or negatives to write. How about this guy? Here's the oxygens, and it's next to a positive carbocation. So remember, this is an empty orbital, sp2. That tells me that a pair of electrons can form a pi bond, and when it does so, there's one set of electrons left on it, and now a double bond satisfying the carbon's 4 bonds that it requires. But now oxygen has 1, 2, 3, 4, 5 assigned electrons. It would like to have 6, so it's left with a +1 charge. We got it. The fourth pattern is a pi bond between atoms of different electronegativity. I mentioned, for example, between carbon and oxygen. Oxygen, of course, is much more electron rich, leaving the carbon electron deficient. That's the definition of the polar bond. The electron distribution is being pulled towards the top. So we have really two extremes, and this rarely occurs, but causing the pi bond to be unequally shared. That pi bond can be distributed to create formal charges, and we have no formal charges. I would say this is the major contributor, but this is a valid resonance structure. So for example, remember there's a pair of electrons on the nitrogen. They're not there, but we know they are because nitrogen has no formal charge. It has to have 5 electrons assigned to it. Here we have a double bond assigned around that nitrogen. Which one is the more electronegative element between carbon and nitrogen? Well, clearly nitrogen is electron rich, right? And that makes this guy electron deficient. The polarity of the bond is in this direction. So in terms of the arrow would show the pi bond going to the nitrogen, the more electronegative element. That would give us a single bond on the nitrogen, 2 sets of dots, and there's that bond leading out to that other carbon. This gives us a carbocation and a negative formal charge on the nitrogen. Again, I would say no formal charges is the major contributor. This is valid, but due to formal charges, it's a minor contributor to the resonance structure. How about one more? Doing your homework for you. Notice this oxygen has 2 sets of electrons, making it very electron rich, and the polarity, the bond pulling that group towards it. So that means in terms of resonance, the pi bond can collapse and form sets of dots on the oxygen. 1, 2, 3, 4, 5, 6, giving us a single bond to oxygen, giving us a negative formal charge on O and a positive formal charge on carbon. These two are in resonance. This would be a major contributor, no formal charge. This would be a minor contributor due to the formal charge. And the fifth and final pattern of resonance pattern recognition is the conjugated pi bonds in a ring. And we happen to show benzene. Benzene is a 6-sided 1, 2, 3, 4, 5, 6 alternating double, single, double, single, double, single. We call that conjugated. And really it's as easy as moving them between let me just say, right now they're between carbon 1 and 2, 3 and 4, 5 and 6. The double bonds are located between 1 and 2, 3 and 4, 5 and 6. But now, not by twisting the molecule or anything, now notice that they're between 2 and 3, 4 and 5, and 6 to 1. So we didn't just simply twist the molecule and kind of shift it clockwise or counterclockwise. We actually broke bonds and moved bonds in order to create the resonance structure. Draw the resonance structures, including all lone pairs. Well, for this particular molecule, the oxygens require lone pairs. The nitrogen needs a lone pair. And this is the aromatic functional group called benzene, and it is really the only alternating conjugated system. So when I think about redrawing this, all I'm really going to do is to shift the positions of the double bonds and redraw the molecule just with the positions of the double bonds shifted by one position, clockwise or counterclockwise, doesn't matter, you'll get the same picture, but everything else is identical. And so when you do that, you're just going to draw in those arrows as I had shown. This is the answer key to your homework. Make sure you remember that the oxygen gets 2 sets of lone pairs, the nitrogen gets 1 set of lone pair, and that you've just shifted the position of the double bonds. They were between carbon 1 and 2, between carbon 3 and 4, and between carbon 5 and 6. Now notice where they are. They're between carbon 2 and 3, 4 and 5, 6 to 1. And so you're just moving the position clockwise or counterclockwise. And you can shift these with your arrows. It's okay to go this direction. And it's absolutely okay to go this direction. So just pick clockwise or counterclockwise when you're drawing your arrows in your homework. So here's a summary of those 5 patterns that you need to work to memorize, to recognize, and be able to manipulate in order to practice resonance structures. We talked about an allylic lone pair. The allylic position, these are the 2 carbons in the double bond. The lone pair must be 1 position away. Remember that this is a delocalized pair of electrons, and 2 sets would be localized. You're only allowed to move 1 set of electrons. We had an allylic carbocation. Remember, this is an sp2 empty orbital, so it will happily accept a pair of electrons. A lone pair adjacent to a carbocation. Again, this is an empty orbital. It will happily accept a pair of electrons. Notice this, I should stress, 2 sets of arrows, 1 arrow, 1 arrow, 1 arrow if we have an electronegativity difference based on polarity. And here, in a cyclic structure such as benzene, to move all 3 of those bonds that are conjugated, we ended up using 3 curved arrows. And that's going to take a little bit of practice. This is what, a lot of the homework here in Chapter 2 is about resonance structures. So draw resonance structures for each of the following compounds. So what pattern do you recognize? Here I have a double bond, and adjacent to it is another double bond. So that double bond really has no place to go, does it? It has no positive, no pair of electrons. It doesn't have an empty orbital. So this right here is a very localized double bond. However, this double bond, based on polarity, we recognize a pattern that says, due to the electron distribution based on electronegativity difference, I'm able to move this set of electrons, which I put a green dot there, and create a set of dots and a negative formal charge on the oxygen. So that pi bond is delocalized. Here I'm noticing a conjugated set of bonds, and I notice it next to a positive sp2 carbocation. So this is going to have a first set of arrows in which the pi bond can shift over. And when it does so, this bond stayed the same, the pi bond shifted here, and the carbocation is now at carbon 3. We now recognize that this pi bond is then able to do the same thing. It can shift, forming a third resonance structure. First bond here, next bond is now here, and the positive ended up at the very end. So there were 3 structures where the allylic position was a carbocation. Again, you're going to have lots of practice, no worries. Well, you know what? It looks like I missed this position. This double bond does indeed exhibit resonance structures for each of the following compounds. I'm so glad I spun ahead because look now. Got it. You probably are coming out of your seats ready. This carbon, I neglected to put a positive carbocation there. It only has 3 bonds. I am so sorry I missed that. Oh my goodness, embarrassing, because now this allylic position, this double bond, does indeed meet the criteria of being next to a positive carbocation. Duh! Which means the pi bond can then move, and we would have, here's the negative. The pi bond now is here, and the positive charge has moved over here on that particular carbocation. Come on up, Bubby. So now there are indeed 3 structures for this one as well. Yep. So the first structure didn't meet the criteria until I put a carbocation next to it, and now it delocalized. This pi bond now meets the criteria of being delocalized because it's got a neighbor of a positive carbocation and therefore it can shift positions. So all 3 are valid resonance structures for both A and B, having 3 valid structures. When we assess resonance structures, we look at the hybrid between them and decide which one of those really is the major contributor and which will be the minor contributing structures. When multiple resonance structures can be drawn, we know a blend of them all occurs called a hybrid. But typically not all the resonance structures contribute equally. So let's go through some following rules and kind of list in order of importance to give us, how to determine the most significant, which I've been calling the major contributor, which are less significant, which we call the minor contributors. Rule 1, when assessing the best structure for resonance, the one that is the major contributor to the blend of the hybrid, the most significant resonance form have the greatest number of filled octets. We want all atoms, if possible, to have an octet. Notice here, for instance, this carbon has an sp2 hybridization. It has an empty orbital. That empty orbital means that it only has 6 valence electrons or 3 bonds. If I were to move that, and as it did here, move a pair of electrons, look now, this carbon has 4 bonds. This oxygen has 3 bonds and a lone pair. That means all of them are obeying the octet rule. That is a better structure. If you obey the octet rule, that's a major contributor, rule 1. Rule 2, in determining the major contributors of the hybrid structure of a resonance, says the structure with fewer formal charges is more significant. And I might have been saying that all along. It says If I have 0 on all atoms for formal charge, that would be the major contributor. If I have formal charges, on the nitrogen here is a +1, over here the nitrogen is a -1, it is a valid structure because all are obeying the octet rule. And the nitrogens kind of balance one another out. I have a +1 on one and the negative on the other, so overall it's 0. And that's okay. That's a major contributor. That's a valid structure. But what makes this one not valid is that it does not have a full octet on this carbon. It's an sp2 carbon. So the first two structures have full octets. The first one, of course, has no formal charge, so bing, that's the largest contributor. The second obeys the octet with formal charges, so okay, that's good. But the last one is a very minor contributor, even though it's a valid resonance structure because it's obeying the way to move electrons. It's going to be the minor contributor because it has an empty orbital on the carbon. If the compound has an overall formal charge, focus only on drawing resonance that form and show the delocalization of the charge. So I'm allowed to move a pair of electrons into a pi bond. I'm allowed to move a pi bond and form a pair of electrons. I'm delocalizing the negative charge. But what have I done to move to this? This being a non-valid structure. Again, I'm seeing that it's an sp2 hybridized. I'm seeing here that I have -2 overall on this oxygen here. So I really haven't accomplished much with this last move. By taking the set of electrons and moving this, when I'm done, is move this back up. That's how I got this third structure. And doing so really accomplished breaking the octet rule for the carbon, and I wouldn't want to do that. So only 2 really major contributors, and the following is insignificant because moving that last set of electrons back kind of made a positive charge on the carbon. Bad move. A structure with a negative charge on the more electronegative element will be significant. The structure with a positive charge on the least electronegative is also valid. So in other words, if I had carbon as a negative formal charge compared to oxygen with a negative formal charge, clearly oxygen is more electronegative, and therefore it should exhibit the negative charge, not the carbon. Here we have a positive sign on the oxygen, and here we have a positive sign on the nitrogen. Now, who's more electronegative between N and O? Remember in our periodic table, C, N, O, F, as we move across period 2, the closer you get to fluorine, the more electronegative you are. And so we'd want the positive on the nitrogen, which is less electronegative, than the oxygen, which is more electronegative. So the positive sign belongs on the least electronegative. The negative sign belongs on the more electronegative element. That creates a more major contributor to the resonance structure. If you had to rank the resonance structures from most to least significant in this example, what might you say? All right, so they're all valid resonance structures as you're examining them. I notice letter A places a negative formal charge on oxygen, and letter B places a formal charge of positive on the nitrogen, which is good because this is less electronegative. This is more electronegative in terms of oxygen compared to nitrogen. Nitrogen is less electronegative than oxygen, so it should bear the formal charge of positive Oxygen should bear the formal charge of negative. How about letter B? Well, I'm upset about letter B right off the bat because I have an empty orbital, so I'm breaking the octet rule. How about letter C? Now you know, C looks nice, doesn't it? All octet rules, I mean, everybody has 8 electrons, that's good. Carbon has 4 bonds, oxygen has 2 bonds, 2 sets. Hydrogen, yep, this is perfect. No formal charge on anybody, and the octet rule is being followed. Excuse me. So I like C as the most, followed by A, because it has a good octet rule. The octet rule is being followed, except it has formal charges, but that's okay because the negative is on the more electronegative element, so that's good. And then the least would be letter B with that empty orbital. And that's what we verified here. The major contributor is letter C, filled octet on all, no formal charges at all. Number 2 would be the structure A, filled octet on all formal charges, negative on most, electronegative element, and the least minor contributor would be part B because of that sp2 carbon, only 3 bonds there. And so that's kind of the homework part here, is drawing the significant resonance forms for each compound below and indicate the major resonance. So if I have a negative on the nitrogen, it means it has 2 sets of dots on it. I can move a set of dots to become a pi bond, and when I do so, I form 1 hydrogen leading out here. It now has a double bond, 1, 2, 3, 4, 5. And then of course I can move these guys around and I can have the double bonds appearing this way. So which is the major contributor? 1, 2, 3, 4. 1, 2, 3, 4, 5. That's not a valid. How did I know that's not valid? Because this here gives me 5 bonds on this carbon. So that's not valid. What if we only moved the first pi bond and left the resonance structure as is here? Right, so instead of these arrows, did that accomplish anything? The answer is no, because this carbon still has 5 bonds, so that's no good. So the pair of electrons on the nitrogen really don't move. They don't produce a valid structure. So the only type of resonance structure that could occur for this is really just moving the conjugated pairs, such as this. And when we move the conjugated pairs, we still end up with the same structure. So those are equal valid structures. How about the letter, or the next example here? 1, 2, 3, 4, 5, 6. Double bond. Here's an N to an H. All right, so I have 1, 2, 3. I know that there's a lone pair on the nitrogen. Here's a positive sign here. All right, so I better give myself, yeah, I'm going to just redraw that so I have some room. Cyclic NH. And just to remind ourselves, this is where the double bond was. And we had a positive sign directly here. Okay, I just wanted to redraw and work this through. We had dots here So notice that we have a double bond and the allylic position is a carbocation, which means I can move this and the position then changes where the positive sign becomes. So now the double bond is here and this becomes here. Now all of a sudden I have a double bond adjacent to a lone pair of electrons. So we can move again. And this particular structure says the dots here, this is an H. There we go. All right, so we have an adjacent pair. So that means this particular structure can move those dots to become a pi bond. This is just where that is. Now notice these dots will never go this direction, never ever, because hydrogen will never form a double bond. So this here will come in as a double bond, and this then will form a lone pair. So the double bond now is here, the double bond lone is here, and that positive charge has been removed because we have filled the empty orbital. This carbon, who only had 3 bonds before, now has 4 bonds. Remember, there's a hydrogen there. Even though it's not drawn, we know it's there. So that carbon went from sp2 to sp3. Therefore, we got rid of the positive charge. Nitrogen has 1, 2, 3, 4 assigned electrons. So the nitrogen should have a +1 charge. What's the most significant resonance structure? And that's really what you're asking yourself. So the first structure had a positive charge on the carbon. The second structure has a positive charge on the carbon. And no formal charge on the N or the H, right? That's just all 0. So I'm going to say these two are equal contributors because all we really did was move the positive charge from one carbon to the next. However, in this structure, what happened is that we moved the positive formal charge, which was on the carbon, right? So this is on the carbon on structure 1 and 2. But carbon over here, it's now on the nitrogen, and that's the more electronegative element, not the least. So that would be the least contributing factor. Even though we ended up having an sp3 carbon, we had we still had a nitrogen with a formal charge. We'd rather have the positive formal charge on a carbon than we would on a nitrogen. When we think about resonance and hybrid structures, we're mentioning that they're really a hybrid of both. So this is just a practice to really think about what does it mean to be a blend of both structures. Draw a resonance hybrid, for example, for the following compound. So this is really just challenging us to say, I know that I can draw a new structure by moving the electrons, and in doing so, I've moved them. I didn't just rotate the circle, I moved them. But as a hybrid, I want to show them as a combination of both structures, and that's where we used these dashed lines to represent a delocalized bond. So oftentimes for benzene, to represent the hybrid structure, you'll just see it with a circle inside, and that's telling you, I want you to envision this structure equal bond length in all directions. And the hybrid structure for the carboanion would show an equal distance from carbon 2 to carbon 3, as well as carbon 2 to 1. So again, you're just using a dashed line to represent equal distribution. We're heading to the home stretch, looking at delocalized lone pairs. Recognize when it means to be localized, which is not involved in resonance, and the term delocalized, which means they are involved in resonance. And remember, to be delocalized, a lone pair of electrons must be adjacent to an atom with an unhybridized p orbital. The lone pair on the nitrogen is delocalized because it's next door to a carbon with a p orbital. These sets of electrons, this carbon is sp2 hybridized, right? It has 3 electron domains, 3 are bonded, 0 are unbonded. 330 is trigonal planar. That meets the criteria of being delocalized, which means we can really set in these arrows as saying this pi bond becomes a set. The lone pair can become a pi bond, and that resonance structure would give us a carbon leading up to an oxygen, now with a negative formal charge, leading down to the nitrogen, which then donated a pi bond, leading R. And now, of course, nitrogen as 1, 2, 3, 4, this would become a positive charge. Now, of course, this would be the major contributor with no formal charges, obeying the octet rule. This would be a minor contributor, but still a valid resonance structure. So the lone pair of electrons on nitrogen are delocalized. Remember, these 2 sets on the oxygen, they did not move, so they're considered to be localized. On oxygen, it would only be the 3rd set of electrons that could be delocalized as we move back to the original structure. So in one structure, that nitrogen is sp3 hybridized, and the other indicates that nitrogen is an sp2 hybridized, right? So here is sp2, here would be sp3. Which one is it? And the answer is yes, it's sp2. It is a delocalized set of electrons and therefore can be involved in resonance structures. So to be delocalized, the lone pair is involved in resonance. If it is considered to be localized, it is not involved in resonance. So let's say, for example, here is a lone pair of nitrogen on the nitrogen atom, and we see that it is in the allylic position because here's a double bond, and yet I really can't draw a valid structure because this is already an aromatic compound. It has that conjugated positive negative. So this is not a valid structure since this ring is already aromatic. The lone pair in this molecule cannot overlap to the adjacent. So this lone pair ends up to be parallel to the axes instead of perpendicular to the axes. So these are localized electrons.